RI Xmas Lectures, Program 1, VTC 6HTBO 3066. 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3.
I've got here an external combustion engine, and you, like I, are all internal combustion engines. So the only difference really is that in an external combustion engine, as you see here, the fuel is being burned outside the engine. In an internal combustion engine, an internal combustion engine like you or me, the fuel is burned inside. Now, most engines which we are familiar with these days are internal combustion engines, like car engines and diesel engines and so on. And we are not unnaturally concerned about their fuel consumption. Now, in these days when petrol is expensive, the first question we would ask when buying a new car is how many miles does a gallon will it do? We are really asking a question about its fuel consumption. And the way we would find out would be to put a tiny tank onto the car holding a pint or two of petrol, and we'd take it out on the road, and we'd drive it along the road until it ran out of petrol. And we could do a very simple sum and we'd get the answer. Now, you can't do the same sort of thing to me. You can't give me a small sandwich and get me walking along down the road and find out how long it would take me to die of starvation. So obviously, it isn't quite as easy to measure the fuel consumption of people or animals as it is of engines. Now, you may ask, who wants to know anyway? What is the use of knowing about the fuel consumption of people? Well, let me give you just two reasons, and there are many more. Let us say you're running a factory or an agricultural process, and there's a question of changing the mode of operation of the kind of machinery. You might well want to know whether a particular kind of machine is more or less stress on the worker than another one. And one way of finding out, apart from obviously asking the man, is to measure how much energy he's actually using operating machine A as distinct from machine B. But quite apart from that, there's a perfectly good medical reason for this requirement of information. That is that in all developed countries these days, the question of overweight or obesity is a major problem. Now, we don't yet entirely understand why two people eating apparently much the same amount of food, one of them gets fatter and fatter and fatter, and the other stays thin. And this obviously has something to do in the relationship between how much energy is used, how much fuel is burnt inside this person, and how much is put into store. Now, this lecture, which is one of 6, is very much concerned with finding out in a way which doesn't involve making a hole into me or into a person, how much energy is actually being used at a given time. Now, let me first show you a slide to give you some idea of the sort of chemistry which goes on inside us. It's really very simple. We take food, we combine the food with oxygen, which means we burn the food, we produce carbon dioxide, we produce water, and we produce some energy. And here underneath, I've written an equation for those of you who are chemically minded, where we take some glucose, which is a very common food which is being burned in our tissues, and we combine it with oxygen. We produce the same volume of carbon dioxide as the volume of oxygen which we've used. We produce some water, and we produce this mysterious figure of 2,835 kilojoules. And that's for a moment what a joule actually is. It is merely a way of describing a quantity of energy. It's not like having a bucket of water. Having a joule is a measure of how much energy we've got. We produced 2,835 of those. And those of you who prefer to work in calories or kilocalories rather than joules, we merely have to mentally divide that figure by about 4.18 to be exact, to get into the more familiar calories. So the combustion of this amount of glucose will produce about 700 calories. But to make this even more graphic to you, I've worked out another sum where if you took about 10 grams or 2 teaspoonfuls of glucose, and if there was some way of converting it entirely into electricity, you would keep a 40-watt bulb alight for just about 1 hour. So this just gives you some idea how concentrated a form of energy we have in fairly and quite common foods. Now, this kind of combustion goes on inside me. But just to show you that I'm not in accelerated time, I've been provided here by the Royal Institution in a number of delicious sponge cakes. And just to show you that there's nothing fake about these sponge cakes, I've got a courageous young lady here who's actually going to eat half of the sponge cake to convince you all that there's no ill effect, there's nothing special about this. Just eat half of it and tell us what it tastes like. What? No ill effect, no immediate ill effect. It's good? Right, well, let me have the rest of it back. I keep a bit of it, and the rest of it I put onto this clip here, and I'll dip it into liquid oxygen. And you'll see in a moment, in very much accelerated time, the kind of process which goes on rather more slowly inside me. And remember that the things which we get are a certain amount of useful work, and I suppose some of you might imagine that I'm doing a certain amount of useful work at the moment, a great deal of heat, which you could feel if you put your hands on me, and a certain amount of steam. Now, Mr. Bill Coates is now going to set fire to this, and there should be a rather interesting effect. Now, I'm not pretending that however much fire I have in my belly, it really goes on at quite a set sort of rate. And if this were served to me as a flambé meal in a restaurant, I feel I would be rather disappointed at the amount which was actually left on my plate at the end. But basically what has happened there in a very short time, I suppose we must have burnt about 100 calories worth, is what happens rather more slowly inside me. And if we were able to measure this, there would have been some carbon dioxide and some water vapor, a good deal of heat, and some light. Now, what we're going to do this afternoon is to work our way up to the point where we can actually make the measurement of the fuel consumption on somebody riding a bicycle or somebody sitting in the audience. But before that, I must introduce you to the actual tools of my trade, the instrument which I'm going to use. And first, we have here, this black box is an oxygen analyzer. And what it does is that it will indicate on this dial here the percentage of oxygen which is in the air which we are breathing at the moment. Now, it's indicating something like something approximating to 21% at present. In the inspired air, in ordinary natural free air, fresh air all over the world, there's something of the order of 21% of oxygen. And this is true in the deepest valley and at the top of Everest. And you've got to have a pretty stuffy room, and it looks like we've already depleted our oxygen concentration slightly in this room here before you get appreciably below that. Standing immediately underneath it here, I've got a carbon dioxide analyzer, an infrared analyzer, which just in the same way as the oxygen analyzer will indicate the percentage of carbon dioxide in the ambient air. And we are up to something like 0.06%. In absolutely fresh air, it would be more like 0.03%. And remember, these 0.03% are very important because this is the carbon dioxide which the whole of the plant world uses in synthesizing, with the help of sunlight, the carbohydrate on which all other life is dependent. But because obviously there are something like 300 of you madly breathing out carbon dioxide at the moment, we've already managed to increase the concentration of carbon dioxide in this room. And further along here, I have two gas meters. Now, these gas meters are exactly the same sort of gas meters which you have in the cupboard under your stairs at home, except that they're fitted with a much larger dial, and you don't have to have a special man to come and read them, because one of you is going to help me read it afterwards. Well, just to show you what these gas meters are capable of doing, I have a volunteer here who's going to catch some of her expired air in a balloon for me. If you just blow this balloon up to about the size of your own head, that will do fine. Thank you very much. Now, if I've been telling you the truth, there should be some carbon dioxide in this, and there should be rather less oxygen than there was previously. So I'm going to get my analyzers. I'm going to suck the air out of here. It's going to take a little time to get through to the analyzers because it's got to fill all the tubing, and the analyzers take some time to respond anyway. You see, we've got something like 3.3% of carbon dioxide, and the oxygen concentration has been depleted to about 18% or so. Now, I'm going to do the same sort of thing myself, but rather more rigorously, show you what can be done by filling this bag with my own expired air. And I'm going to rebreathe this air several times, rather as if I was trapped inside a submarine, for instance, where I had to use the same air over and over again. I'm already quite out of breath because I've used the same air. Let's see what sort of oxygen depletion I've managed to get into that, and what carbon dioxide concentration I've reached. Again, it's going to take a moment or two. There we are. The carbon dioxide is rising very satisfactorily. Yes, I've made over 6%. It's the best I've managed to do so far. And the oxygen is plummeting down to 12% or so. Now, the interesting thing about this is I'm really still quite out of breath because I was getting noticeably short of oxygen, rebreathing the same air, and breathing in carbon dioxide stimulates one's respiration. This is about the sort of quantity of oxygen in a given amount of air which you might find at the top of Everest. So I was breathing air which didn't contain, in terms of grams per liter, more oxygen than time Everest, and there's no wonder, therefore, that I was getting a little bit short of sort of puff whilst I was doing this. So here are the three tools which we are going to use. And we are going to try and alternate explanations of how these instruments work with actual experiments. And I think I should perhaps say at this point, this being the first lecture, that what these lectures really are all about, the signals from the interior, is to emphasize to you that whilst a car mechanic can take a spanner and a hacksaw and all sorts of things and take his engine to pieces to make measurements, by and large, I am not allowed to do this to you. And therefore, I have to find means of getting the sort of information from your inside without actually doing you any harm. Doing it, as the engineer would say, non-destructive testing, or as the doctors would say, non-invasive measurements. Both comes to much the same sort of thing, that I don't actually have to make any holes or break the skin to find out what goes on inside you. So let's start off by learning how the infrared analyzer here works, which is really very, very clever and elegant piece of equipment. But before we can go into the details of this, we have to learn a little bit about just ordinary optics. Now, what I've got on the screen here is a spectrum of white light. You can see this. You can see the spectrum here. It's white light split up by a prism. At one side here, we've got the violet region rather, of the spectrum. At the other end, we've got the red region. If you went past this end, we would come into the ultraviolet. If you go past this end here, we will come into the infrared. Now, I'd like you to remember about infrared in particular, because we should be using that in a moment. I'm now going to ask Bill Coates to put a tank containing a pink liquid. It's really a very dilute solution of potassium permanganate in the beam. And you'll see that it's left the blue portion and the orange portion and the red portion of the spectrum virtually untouched, but it's absorbed most of the light from the green and the yellow portion. Can we just move it in and out a few times? See, these portions stay almost unchanged, the yellow and green portion get absorbed quite strongly. Now, what do you think has happened to the energy which should have been in the green and yellow portion of the spectrum? It's been absorbed by the liquid in the tank. And what do you think happened to the energy itself? Would the water in the tank have got hotter or colder? Hotter. That's right. Now, if I had used an increased concentration of potassium permanganate in the tank, so they would have absorbed or stolen more energy from those sections of the spectrum, would it have got even hotter or not quite as hot? Would have got even hotter, right? So in theory, at least, I could make myself a piece of equipment for measuring the concentration of some colored substance dissolved in water by measuring the kind of temperature rise which I would get. Now, in practice, this would be very difficult to achieve because water has a high specific heat. This means it requires a lot of heat to raise its temperature by a measurable amount, and the effects would be rather small. But we can do this with gases. And this is the principle on which the infrared gas analyzer operates. Now, this slide, which I've got here, is really a plot of how much light is transmitted from nothing to 100%, plotted against the color of the light, or the wavelength of the light. Now, the visible part of the spectrum is somewhere around, has a wavelength of somewhere around half a micron. About half a micron would be yellow. So the part which we can see is in this region here. The red is just below the 1 micron, and anything longer than that is beyond the red, is in the infrared spectrum. Now, we aren't used to gases being colored. Some of you might know that chlorine is green and bromine is brown, and one or two other gases have colors, but by and large, we think of gases as being totally transparent. Well, if we had infrared eyes, and we were looking at a tube full of carbon dioxide, we would find it as colored just as much as a tank of potassium permanganate was colored, because it absorbs strongly of a wavelength of 2.8 microns about, and again strongly at about 4.3 microns. So we'd have a colored gas here, and therefore if we had a volume of this gas and we shone infrared radiation through it, it would get hotter just as the tank of our pink liquid would have got hotter had we had a sensitive enough machine to measure it. Now, this is a principle by which this machine works. And let me just explain to you how. And I'm going to rely very much on your cooperation to tell me the answers to questions which I'm going to put you. What I've got here are two aluminum tubes, and each of these aluminum tubes is divided into two compartments by windows made out of material which is totally transparent to infrared radiation, just as transparent to infrared as window glass is to ordinary light. Below these tubes, there are two little heaters, which are run just like tiny electric fires at a dull red heat, which emit infrared radiation. And the top chambers, which are airtight, incidentally, these chambers are all gas-tight, is connected to the two sides of a pressure gauge, which can measure differences in pressure between the two sides. So at the moment, we've got the infrared radiation going through. It's not being absorbed by anything. The pressure in these two chambers is equal. If I now were to put some carbon dioxide into this chamber, and if I had wired this pressure measuring meter up in such a way that the pointer went that way if the pressure was higher here, and went the other way if the pressure was here, if I put some carbon dioxide into here, would the pointer move to the left or to the right, as seen from you? To the right, right? And let's see whether you are right. Yes? Here's the carbon dioxide in my little orange dots. It now steals some of the energy, gets itself warmer, it expands, and the pressure in that side rises. If I were now to put some carbon dioxide into this side as well, the same amount of carbon dioxide, in which direction would the pointer move? Left. Let's see if that's right. Yes, you're right. In fact, it went right back to the middle. And now the most important one. If I were to put the gas which I want to analyze into this compartment here, the gas like my expired air, which contains some carbon dioxide, into this compartment here, it would steal some of the radiation which would otherwise have gone into warming up that upper compartment. So which way will the pointer move now? To the left or to the right? Well, let's see if you've guessed correctly. Yes? And the more carbon dioxide there's in here, the more of the energy will have been stolen, the greater will be the pressure unbalance. So you see here you have got the basis of a gas analyzer that the higher the concentration in here, the greater will this pointed deflection be. But the really elegant part of this analyzer, which was incidentally invented in about 1940 by a German called Luft. Luft is German for air, rather an appropriate name. He's still alive, and he spent most of his life designing infrared gas analyzers. The really elegant part of it is that for all those gases which have infrared absorption characteristics, you can change the specificity of the analyzer, that is, whichever gas it's sensitive to, merely by filling these detector chambers which a gas you're interested in. So if you wanted to turn it into a carbon monoxide analyzer to analyze the exhaust gas from cars, all you'd have to do would be to put a little bit of carbon monoxide in those two top chambers. If you wanted to make it into a nitrous oxide analyzer, because you happen to be an anesthetist, and nitrous oxide also absorbs infrared, you fill those detector chambers with nitrous oxide, and you've now got a nitrous oxide analyzer. So by using the gas itself to detect itself, a principle which I call setting a thief to catch a thief, because they're both thieves in terms of stealing some of the radiation, I think is really a very elegant principle. Well, now let's do our first experiment to see whether I'm right in my contention in being able to forecast merely by measuring carbon dioxide concentration and air flows how much fuel is being burnt. Let me show you my next slide first so that you can what I'm going to do is to burn some alcohol in a special piece of machinery, which I'll explain to you in a moment, and I'm going to measure how much carbon dioxide is going to be produced. And the only figure you've really got to remember is that by burning 1 gram of alcohol, I produce 0.97 of a liter of carbon dioxide. Now, I need an accomplice, or rather a collaborator, who's good at arithmetic. And what I'm going to do, come along. And what I'm going to do is I'm going to ask him to weigh this little bottle of alcohol here, and I'm going to get him to write the weight of the bottle of alcohol onto that piece of paper and show it just to you and not to me, because he's going to be allowed to weigh the bottle before and after I've burned some of it. I'm only going to be allowed to look at the concentration of my gas analyzers and calculate how much alcohol should have gone, and I see how good an answer I can get. So I'm going to retire behind my machinery. Right? So you write it down on there, and don't let me see it. Can somebody tell me, because I'm going to ask you to read the carbon dioxide analyzer. Is it reasonably near naught at the moment? Right? Good. So can I introduce you to my alcoholic friend here, who only metabolizes alcohol, unlike me. I'm now going to clip this bottle of alcohol into here. I've got a little electric spiral on here, which, if I can get it in the right place, is going to light the wick for me in a moment. I'm going to blow air through he's now breathing, and I'm going to put the pipe. Can you hand me the tube? Thank you. Thank you. I'm going to poke this tube down his mouth, so I can estimate how much carbon dioxide is coming through. I'm going to allow 60 liters of air to go through here after having lit the flame, and I'm then going to do some sums. So I'm going to light the flame now, and I'm going to remember what on my gas meter, use the same gas meter which you can see here. Right, the flame is lit, and we're now going to allow this to burn for about a minute and a half. And at the end of this time, no, you mustn't let me see this. In a minute and a half, I'm going to put the flame out again, and I'm going to do my sums. In the meantime, I'd like you to keep an eye on the carbon dioxide analyzer, because I've got to rely on you to tell me what the highest reading on the analyzer is going to be. You can probably either see it on here, or you might be able to see it on one of the television monitors. Now, the things which are happening inside this bottle are exactly the same things which are happening inside me. It's growing warm, quite measurably warm, because we're producing heat. You can see the inside of the bottle is beginning to steam up, because in addition to producing carbon dioxide, you're also producing water vapor. But he isn't doing much useful work, is he? He isn't even doing as much as talking to you. Now, the kind of calculation which I'll have to make in a moment is that I shall have to take the volume of gas which has passed through here. I shall have to multiply it by a factor which is going to be 0.94 at the moment to correct it to standard conditions of normal barometric pressure and normal temperature. I will then have to multiply it by the carbon dioxide concentration which you're going to tell me to work out the volume of carbon dioxide which has been produced. I'll have to divide that by 0.97 because each gram of alcohol in burning produces 0.97 of a liter of carbon dioxide, and then I should get the results in terms of weight of alcohol. Now let me tell you, just to ensure myself, that it's quite difficult to do these experiments accurately, even with the best possible equipment in the world. So I wouldn't be entirely surprised if I was 10 or 15% out. I would be reckoning I would be doing really rather well. I'm going to blow the flame out in a moment now. I've got another 3 liters to go. Remember, I want you to tell me what the carbon dioxide concentration is. Right? Remember the figure and tell me in a moment. This is where the competition now is. Now you weigh this and do the subtraction. And don't show me the figure. Somebody tell me what the carbon dioxide concentration was. 2.4. 2.4 is the only figure I really want. Now this is a sum which I can't do in my head really at all easily, but I happen to have brought a calculator with me. So I'm now going to do the sum exactly as I told you. We used 60 liters of air. I'm going to multiply that by 0.94 to get the actual volume of air which passed through, which is 56.4 liters. I'm going to multiply that by the carbon dioxide concentration, which was 2.4, and I'm going to divide it by 100 because that was a percentage. This gives me the actual volume of carbon dioxide which was produced, 1.35 liters, and I'm going to divide that by 0.97 to give me the weight of alcohol which I think was produced. It's 1.39 grams. What was it really? Well, I've overestimated. I normally overestimate this because in passing the air through here, particularly at the end of the experiment when I blow the flame out, the whole inside of here is quite hot, and I evaporate some of the alcohol as well. But I've got not too far away from the figure which I wanted to get to. We cover the calculator up again. Thank you. I did this experiment the other day, and to my enormous surprise, I think the figure on the card read 1.01 gram, and I got 1.01 gram. But this only happens once in a lifetime. So at least you've got the principle, which isn't really very difficult, of how one can estimate how much fuel is being combusted inside an organism, using exactly the same means, merely by knowing gas volumes and gas concentrations. Now let me tell you the second bit of physics about how the oxygen analyzer works. But we must learn a little bit about magnetism. If I were to give you a tray of assorted objects, buttons, thimbles, keys, coins, and so on, and a magnet, and you were going to wave this through the tray, you would really classify all the things in the world as being either attracted to a magnet or not being attracted to a magnet. They either be magnetic or non-magnetic materials. In fact, there are really three families of materials. Amongst those which you would have classified as being non-magnetic, there are 2 classes. The vast majority of materials are what is known as diamagnetic. That is, if you were to put them into a very, very strong magnetic field, they would actually try to get away from the magnet. But this effect is so tiny under all ordinary circumstances that you wouldn't normally notice it. There is a much smaller class of substances which are called paramagnetic. And those, in a much, much smaller way than iron, would also be attracted to a magnet. Well, just as it so happens, Faraday, nearly 130 years ago, actually did these experiments to identify both diamagnetic and paramagnetic substances at the Royal Institution. He did this in 1847. And here are actually some of the specimens which he used for these experiments. And the nice thing which he has written, which I will read to you, is he tested even such things as carrot, apple, and meat. He commented, if a man could be suspended with sufficient delicacy and placed in the magnetic field, he would point equatorially. What he really meant there was if you could suspend a man in the way you could suspend a compass needle, very, very delicately and balance him very delicately, instead of aligning himself north and south, as a magnetic or paramagnetic material would do, he would align himself east and west, so as to have as little field passing through them at the moment, through them as possible. And in this box here, specimen number 1, sealed up in this little glass bulb, is the actual specimen of sealed up oxygen, which Faraday used to show that oxygen was a paramagnetic gas. Oxygen is a paramagnetic gas, and is really on this property, which oxygen shares with no other common gas, on which this gas analyzer is based. But let's just look at 1 or 2 more slides first. What I've got here, just to reinforce the properties of paramagnetic and diamagnetic materials, I've got 2 horseshoe magnets here. Here we have a little sphere made of a paramagnetic material. Remember, acting in a very small way of business in the same way as iron. It would be attracted towards the magnet. Here we have a sphere made of a diamagnetic material. Again, the effects are really very small indeed, and it is actually repelled away from the magnet. Now, on the next slide, I've got a table of the properties of the common gases. And here you can see that oxygen, in comparison with anything else, is enormously paramagnetic, that air is paramagnetic in proportion to the amount of oxygen which it contains, about 1/5 as much, 21%, but that all the other gases in which we might be interested, like carbon dioxide and hydrogen and nitrogen, are diamagnetic, but really to a very, very small extent. So that for all practical purposes, if we can measure the paramagnetic properties of air, we are measuring how much oxygen is contained in the air. Now, you might not believe me. You might not believe me that oxygen actually is magnetic, because it is really quite difficult to demonstrate. Because normally it isn't dense enough. You can't get enough of it clustering around the magnet to show. But what I've got here is some liquid nitrogen. All this is always rather spectacular. And I've also got some liquid oxygen. And I don't know whether you can see this, but liquid oxygen has a rather pretty light blue color. Now, these liquids are very, very cold. The boiling point of liquid nitrogen is minus 195 degrees centigrade. So if I dip this magnet into it, there'll be furious boiling at first, because the magnet is, of course, very hot compared with the minus 195 degrees centigrade. And I'm going to pull it out in a moment, and we can see whether there's any nitrogen stuck between the poles of the magnet. Because if the nitrogen was at all magnetic, it would be attracted to the magnet. We've got some bits of paint in there. This doesn't show the effect very nice. I have to do it again. Let me cool it down again. It's the contraction of the paint. The paint goes very brittle at this very low temperature, and we get little bits of paint sticking onto it. Another bit of paint. Anyway, there isn't very much between the poles of the magnet. If now instead I dip it into liquid oxygen, having now well cooled the magnet down, there's quite a nice slug of boiling liquid oxygen. You can see there, trapped between the poles of the magnet. You can see it boiling away, the very cold gas falling away from between the pole pieces. I rather like doing this, so I do it again. Yeah. In this way, in a small way, liquid oxygen behaves rather like iron filings, or liquid with iron filings suspended in it, and being attracted by a magnet. So this, I think, might demonstrate to you that if one gets enough of the oxygen together in a small enough place, it does demonstrate its magnetic properties. Now, how can we use this to actually make an analyzer for oxygen? And I've got here a model which is a very much enlarged of a measuring cell which is on the inside of this machine here. Now, what we have are really two enormous horseshoe magnets. Imagine the horseshoes coming along the back here. And the pole pieces of these horseshoe magnets are made very tapered. So would you expect the field between here to be stronger or weaker than outside here? Stronger, exactly, because the pole pieces are closer together. Now, this dumbbell here is made of very, very light spheres of a diamagnetic glass. Now, diamagnetic materials want to get away from magnetic fields. So which way do you think this thing will want to twist? This way or that way? What is this way? This way here, right? Because it wants to get away from the stronger parts of the magnetic field into the weaker parts of the magnetic field. And the twist is finally balanced by the winding up of the wire which suspends this so that it comes to rest in an equilibrium position. If we were now to fill this whole chamber here with a gas containing oxygen or even pure oxygen, because oxygen behaves to some extent like a magnetic material, the field in here would actually become stronger. Because the field becomes stronger, the repulsion which these diamagnetic spheres experience becomes even greater, and they rotate further out of the field. So if we had a means of measuring the amount of extra twist which was produced, we now have a device for measuring the concentration of oxygen. And in a very crude sort of way, we can arrange that. Now, I don't really think we can make this work. There ought to be somewhere other. What I'm doing now is that there's a mirror fixed onto the suspension here, onto the wire which suspends the dumbbell. I'm going to reflect a light beam from that. Yes, there it is. There's 3 members of the audience in the front row obligingly holding up a screen for me. Now imagine that in a proper instrument, that screen could be graduated in a percentage of oxygen. Therefore, the more this little dumbbell twisted, the greater would be the concentration of oxygen. The further along that way, the light spot would move. Thank you very much. And indeed, there are oxygen analyzers which work in precisely that way by having a little mirror and a light spot moving over a scale, which is calibrated in percentage of oxygen. In this box here, it isn't done in quite such a primitive way, but electronic means are used to translate the deflection of our light spot into actual reading on the dial on the front of the machine or the figures which we have been seen previously. So you now understand, I hope, how the infrared analyzer works, how the oxygen analyzer works, and we can proceed to actually doing a proper experiment where we're measuring the energy expenditure of somebody doing some work. And I'm going to do this in 2 ways. I'm going to measure how much energy it takes to listen to me, which I hope isn't very much. And there is a gallant member of the audience who is offered to be the victim or the privileged person, however you might like to look at it, of this experiment. And what I'm doing is that I'm putting a piece of equipment on his face, which will allow me, you're breathing, right? Which will allow me to measure how much air he breathes out in this time. And I would like some of you to keep an eye on the clock. It's about, if you can like to sit down, if you can tell me afterwards for how many minutes he has been wearing that piece of equipment. Can I just have my next slide? Just very quickly, the piece of equipment which he's wearing is a turbine, which is blown around by his breath. But I'll now fix up the other experiment before I explain exactly how this works to you. Now, we have yet another victim amongst us, another cooperative member of the audience. And we're going to dress him up in astronaut-type gear, the latest in headgear, and a real mask as used in high-flying aircraft, so we can catch all the breath which he's producing. Right. Comfortable? It's one way of shutting people up. They don't answer back. And here we have a bicycle, and this bicycle has the biggest dynamo on it ever, the biggest bicycle dynamo on it ever. If you like just to climb onto this bicycle. And what we can do is that we are going to collect all the air which he's breathing out in this big bag here. And we are going to analyze the air which is accumulating in this bag. So we know how much oxygen is missing from it and how much carbon dioxide is being produced. And we are also going to meter how much air is going into my subject here. Now, if you just like to start cycling, to get used to the idea. He's making electricity, you see. I'd just like you to warm up for a moment. Now, there's one other member of the audience. You come along. And I want to make you, in spite of what I said, that there's not going to be a gas meter reader. These gas meters are simple enough. I'd nevertheless like to have somebody who keeps an eye on the gas meter for me. What I want you to do is to start this stop clock when we get to the 50 mark, and make him work for either 3 minutes or 4 minutes. I tell you how much. So you move this lever here to get the stop clock started at the 50 mark, and you must tell me how many times this thing has gone around. All right? Right, off we go. Right, he's now the situation which we've got now is that he's making 80 watts. He's burning up an amount of fuel which we'll measure. We'll be able to calculate his efficiency to see how good he is in putting the shepherd's pie or pizza or whatever he had for lunch, actually turning this into energy. Remember, I told you that 2 teaspoonfuls of glucose, if we could turn it all into electricity, would have kept a 40-watt bulb light for a whole hour. So we can get we can get those measurements. I again have to rely on some of you to read the oxygen analyzer for me, because I need the oxygen concentration in the calculations which I'm going to make. Now, I promised you that I would explain to you how this machine worked while this experiment was going on, which somebody in the audience up there is wearing. What we've got here is a cylinder, and this cylinder has tangential slots milled into it, so that if air comes in to here, what would you expect to happen to the vein which was pivoted in the middle of that cylinder? It will go around, exactly. And if the vein has practically no friction, then you can make this vein go around at a rate which is very nearly exactly proportional to the amount of air which is flowing through it. So if you then connect this vein through a train of little gears to some hands, that's like the hands of a clock, you can count how many times the vein has gone round. And from that, on this instrument here, which is being worn by our cooperative subject, you can then read how many liters of air have gone through this. The outside hand goes around once every 100 liters. This little hand goes around once every liter. And this hand goes around once every 10,000 liters. So we have a fair capacity in terms of how much air can be handled. Now, how many minutes have we got on here? Have you turned blue yet? Are you comfortable? Now, just to give you some idea, both how much and how little energy is being generated, this 80 watts here is about 6 amps or so at 12 volts. If you found yourself in the jungle, and had to recharge your car battery, you would still have to do this for about 6 hours before your car battery was recharged again. So in some senses, it sounds like a lot of energy. In other senses, it sounds like rather little energy. Are we just coming up to our third minute? Or? To our third minute, right? Right, I'm going to stop in our third minute. Right? Stop, you can stop now. Thank you very much. All right. Let's disconnect you from the machinery. Have you remembered how much? 90. Has somebody kept their eye on this meter? It doesn't actually matter because we've got lots of air. I mean, the reading won't change. Right, Lawrence, you can now dismount. Thank you very much. But stay around because I have a little something to give you in a moment. Now let us do the sum of how much energy has been used. Remember that the concentration of oxygen in ordinary free air is 21%. This reading here is 17. The arithmetic turns out to be mercifully easy because we've used 4% of oxygen from the air. Now, how many liters? Where's my guess? 90 liters, right? So let's work out how much oxygen has been consumed. It's 90 liters. We've got 900 there. 90 liters times this factor of 0.94 to correct it to standard conditions. So the amount of air which has been breathed is 84.6 liters. 4% of oxygen were taken out of that. So let's multiply this by 4 divided by 100. So we've used 3.384 liters of oxygen. Now there's one piece of information which I now must give you, and that is that from many thousands of experiments, it has been found that 1 liter of oxygen is near enough equivalent to 5 kilocalories, or about 22 kilojoules. So if we multiply this by 22 times 22, we've got a number of kilojoules of energy which is actually used inside him. Here we are, 74.448. Now, can we just say this is the energy which has been combusted inside, the amount of food which he has used. Now, the amount of energy which is produced is 80 watts for 180 seconds. So if we can just remember the 74.4, we clear that. That's 80 times 180, this gives seconds, divided by 1,000. So he's made 14.4 kilojoules. And we can now work out his efficiency. So that's 14.4 over the 74.4 divided by 74.4 times 100 equals, his efficiency was 19.35%. This means about a fifth of the energy which we put into him was turned into electricity. Now, this isn't a bad approximation because the efficiency of leg muscles is of the order of 20%. I would have expected an answer which was slightly lower than this, actually, because there must be losses inside the actual machinery in terms of friction and so on. So we wouldn't have been able to convert all the energy from his leg muscles straight into electricity. But it's not an answer which is so very different from that which I expected. Now, he used 74.4 kilojoules. I just happen to know that every one of these of a well-known brand of chocolate beans contains 20 kilojoules. So giving him the benefit that 74 is near enough 80, if I give him 4 of these, he's no worse off than he was at the beginning. I put all the energy. Now, the fact that he did all that cycling for just 4 of those chocolate beans gives you some idea of how difficult it must be to try to slim by taking exercise, because the amount of energy which you use up, even taking quite hard exercise, is really quite small. And anybody who hopes to really get rid of substantial amounts of weight merely by taking a little bit more exercise, like going for walks and things of this kind, is in for a pretty hard and long battle, because just eating 4 or 6 or 10 of those bits of chocolate too much every day would mean quite a hard cycle ride, merely to stay where you are. So here if you like, you've with your own eyes seen one of the sort of experiments which one would like to do from the medical point of view to test. One might want to do in research which is connected with obesity. Now let us also go and have a look at our other volunteer who has just been listening to me and hasn't been doing any work at all, at least only mental work. And mental work is not measurable by indirect calorimetry, as this technique is called. You have been wearing this for about 12 minutes. And you can, let's just stay around for a moment, just over there. And you have been, in these 12 minutes, you've been breathing 120 liters of air, right? So we can, from this, we can now calculate how much energy you've used, and maybe we'll pay you for that too. If we assume that you've extracted the same amount of oxygen from the air which you've been breathing, it's 120 liters times 0.94 times 4 divided by 100. You can't do that quickly, can you? Is the amount of oxygen which he has been consuming. But remember, he's been consuming it in 12 minutes, whilst our bicyclist consumed much the same amount of oxygen in 3 minutes. So he's only been working at about a quarter of the rate. If we multiply this by 22 to make it into kilojoules, we get that he's used 99.2, or whatever it is, 99.3 kilojoules. And that's supposed to be fair. If we divide this by 20, he should have how many of these chocolate beans? 5. All right. He doesn't seem fair, does he? That he does so much better on this than the one who's been doing all the work. At least you can't say that you've been to the Royal Society and we've been exploiting you in terms of making you work without actually paying you back. Right. Now, what have we learned from this? And what kind of information do we hope to get from future lectures in the series? The first one is that it is possible, if you use instruments of sufficient technological complexity, it is possible to measure physiological parameters which are really otherwise very difficult to get at. You would have had to put me into a room in which one could measure all the heat which I was generating, including this I was generating by working, for quite a long time, to measure the amount of combustion which was going on inside me in any sort of direct method. In fact, there is such a technique called direct calorimetry, where people are shut up in very special rooms in which it is possible to measure all the heat which they are producing. Here, we have demonstrated the method which was really very little inconvenience to the subject, made it possible to measure something which was quite inaccessible from the outside. Now, in our next program, our next lecture, we are going to do much the same kind of thing for the circulation. Yeah, we are going to find out how the heart works, how effectively it works, how one finds out how quickly the blood is moving around the body, and what kind of how much at what sort of pressure the blood is being supplied to the tissues. And in future lectures, we should do the same to the nervous system and to the kind of expressions in our face, and even how one can look through the skin. Well, exercise is supposed to be good for you, and electricity is now really rather expensive. So I thought I would do the BBC a favor and generate some of the electricity which they require for their closing credits myself. I'm now making the 80 watts. I'm not sure how long I could manage to go on doing this. Well, goodbye. See you tomorrow.